I'm Van Hauser. You might know my tools, THC-Scan, AMAP, Hydra, lots of article, and our famous website. And you have the pleasure to be the second group to be presented the ipv6 attack protocol suite. But this will not be the only presentation I'm doing. That's why I removed some slides to get it up to speed, because there will be another presentation directly afterwards, which I hope will fit into the time frame. If not, it will take longer. Which will be about another project we are now starting. This is THC-Scan Next Generation. So we don't have much time. I'm just jumping in directly. So what I will do first, a very fast, very fast, 3 slides, introduction on ipv6. I tried to get another hour to do an ipv6 primer, so you understand actually what is ipv6, how does it work. It looks pretty simple at first, but it's very complex. So it will blow your mind just with the 3 slides. So, but CCC said, oh, no time. Our schedule is so full-blown, no chance for that. So, but without, they said, I should assume everybody knows everything about ipv6 already if they're in that room. Sure, yeah. Then I'll show you a quick introduction on the ipv6 attack suite, which will then show you how to exploit the security vulnerabilities in ipv6. There are protocol inherent vulnerabilities, and this is the first toolkit where you can exploit all of them. Well, there is no other tools which exploit them so far, so this is the only one. Yeah, then very shortly, what are the known vulnerabilities, so implementation vulnerabilities so far, but only a very small excerpt, and then what is upcoming research from us and what will be the future of ipv6. So, first, why ipv6? I mean, have you seen ipv6 somewhere so far? Yes, and if you look on our wire here, yes, you will see it. We have, at every time, we have a minimum between 50 and 150 activated ipv6 devices on our network here. Every Linux box, most BSD boxes out of the box run ipv6. We'll come to that later, because this can be interesting. The second thing is, in some companies, it's already deployed. In South Korea and Japan, it's very big. So last month, I did that presentation, a bit longer, in Tokyo on a security conference, because it's really affecting them. They are one of the most numbers of users of ipv6 in Japan so far. But we will see it in about 2 years in Germany as well. Not necessarily on the internet, or internet too, but in home area. So on your kitchen equipment talking with each other, and we see it on the mobile phones. Because T-Mobile and all the others have very big problems with the IP space. You have lots of subscribers, and with services like always on, push to talk and all that stuff, they need to have an IP address all the time. They're using Class A networks, the 10 Class A network, it doesn't fit cross-country. So they need a solution for that, and they will move to ipv6 like Asia already does. So, what is the goals of ipv6? The most impelling one, and everyone will agree, okay, that's why ipv6 is important, is that there are much more IP addresses. ipv4 address space is very small. Also, there's much recycling going on now not to be forced to move to ipv6. But if you see that, it means that every one of us can have several million IP addresses just for every person on Earth. That's pretty cool. So that's why ipv6 was, in the first place, was designed. But just doing more larger IP address space, you can do more if you define a new protocol. And now ipv6 gets very cool. You have auto-configuration of IP addresses and networking. You have in the protocol something like DHCP already included. Like router discovery is all in there. You just plug any device there, and it can talk to everyone else and go on the internet and everything. Auto configuration, that's so cool. You just plug in another router. Nothing you have to do for configuration. The device will automatically, oh, there's a new router, cool. To which address does it go to? Oh, great, let's use it. Auto configuration in the protocol, that's very cool. You can do a hierarchical address structure, which makes administrations or network administration much easier. And you have integrated security features, in theory. I'll come back to that later. Now the security features are there. They're very good. They're effective. But, well, we'll come to that later. So this is the ipv6 header. So if you know how the ipv4 header looks like, and I had to remove this slide because there's not much time, you'll see that it looks pretty similar, but some headers are not there. We'll come to that later. So there's, for example, no IP ID field anymore. You see there is no option stuff in here. You just see source, destination, payload length, what the next header is, could be TCP, UDP, whatsoever, hop limit, flow label, class, and the version. So like ipv4, just these fields being larger and some other stuff removed. Why is that? It's a fixed header. And this is what the routing guys always wanted to have, a fixed header. If you have, like an ipv4, a variable size header, you always have problems with routing packets because you have to know how big is my IP header. And then it's like this, well, bad. So this is why ipv6 has a fixed header, and everything are option headers. And this is very nice. So you have extension headers. So you have your IP header. Somewhere later, you might have your TCP, UDP stuff like usual, and everything which is optional, like source routing, you have in ipv4, you have the same also in ipv6. These are extension headers, and this is pretty cool. So whatever extension you want to have, you just put in there. So this is pretty easy. And if a system has not implemented that special option or extension, it doesn't matter, it just jumps over it, and everything still works. So this is very neat, very clean design. So this is an example how it could look like. You have the IP header, then the TCP header, and then the application data, or a routing header, then a fragment header and stuff. So that's pretty cool. So that's the basic concept. One more thing about the addressing. Your IP address in ipv6 is based on your MAC address, the host part of your IP address. This is the calculation on if this is your MAC address, this will be your IP address. Yeah? There's a privacy extension which makes this random and change this every hour, day, whatever you configure it. So you can have a privacy extension, so your IP address is not reflecting your MAC address. But normally, this is what is done. And it's actually pretty clever because a MAC address is usually unique unless you manually reconfigure it. So there will be no collision in IP addresses. This basic example, if this is your hardware address, this will be the host part of your IP address. Okay, with this knowledge, we can already start. ipv6 were first used by hackers and not by network geeks or whatsoever for special reasons. First, mostly it was used for backdoors. And then enabling IP4 to 6, 6 to 4 stuff, because all the analyzing equipment of the white hats were not able to analyze that. So Lance Spitzner was the first to find that on a honeypot, where a hacker hacked his Solaris box, then enabled 6 to 4, 4 to 6, and, well, hey, Etherreal doesn't show me anything. What can I do? Fuck, what is this guy doing? So this was the first usage, so to hide backdoors and to prevent analysis of the traffic. The other thing is where's exchange, REC bouncing, and stuff. So hackers were really the first users of ipv6. Usually the sex industry is first using something, but here hackers were first. So when we come to hacker tools, what do we have so far? There is not much. And that is what I saw as a problem here. So we have some port scanning tools like Nmap, HalfScan 6. There's a patch for strobe, but they're not working very well. You can have lots of problems because, why does Nmap doesn't let me scan? Well, there are reasons for that, but that doesn't matter. There are some port bouncers, like Relay 6 tunnel, NT 6 tunnels, Azibor, Ninalov service tools, which are mostly connection flooding tools, some packet stuff like libnet and i66. And what I did, I tried to implement the hacker tools for ipv6 to attack the protocol, and I tried to use libnet. It just didn't work. It had not I needed important features which it didn't have. I tried to implement it in libnet, and it was a nightmare. So I wrote my own nightmare. At least I can understand. But all the specific ipv6 stuff, yeah, so attacking the protocol itself, there is nothing. Which got me off because I wanted to play around with that. So I had to code my own. Usually you have to wait until something is widely deployed to have tools available. Well, but I didn't want to wait, and so I'll make this available to you. So it's a very easy to use library. You can do numerous of ipv6 exploits in just 5 to 10 lines of code. All the stuff I will present later, all the tools are already included. There are some caveats in that. First, it's Linux 2.6 only. I started coding it on Linux because that's my favorite operating system. 1 hour later, I thought, let's shoot all the programmers who did that implementation in Linux because it's broken, it's incomplete, and the interface, user space interface, is absolutely fucked up. So it's 2.6 only because I use a proc system, which was the easiest to implement fast. It's Little Indian, 32-bit, and Ethernet only. So you can play with wireless, and here with a cable, Ethernet, wireless Ethernet works perfectly, so this will be no problem at all. For most people, yeah. Some like the 2.4 kernel, some like FreeBSD, OpenBSD, Mac, whatever. Well, you're fucked, sorry. So it comes with some tools. This is just I just showed them some of here, but we get into them later anyway. Implementation is very, very simple. These are 3 lines to generate an ICMP echo request. You see lots of options, and you think, can't this be easier? Does it have to be so many options? Reason is I made it like you can change any single byte in that packet like you want to. So this is why it has so many options. But beside that, very few lines of code. Okay, so executive summary, and then you can sleep the next half hour. ipv4 and ipv6, the implemented security is very similar. So also vulnerabilities are very similar because the basic mechanisms are all the same. I will tell about the other stuff later. So, in the next half hour, I will show you what are the protocol changes, what is reconnaissance, how you do reconnaissance in ipv4, how this will change in ipv6. This is very important because there will be large changes for us as hackers. Local attacks are placed DHCP, how this will be done in ipv6. Smurfing, routing, fragmentation attacks, and finally, coexistence stuff, like we already have here. So, protocol changes. There are 2 things which change, which affects our work as hackers. The first is there is no IP ID field anymore. This was very nice, as in the usual implementations like Linux. You can see when was that machine last booted, because it starts with 0 when you boot the machine, and every second it gets incremented by 1. So, very easy to see when was that machine last booted. Not highly security critical, okay, but it's interesting. But they removed that, so this is not there anymore. And the other thing is, they removed the IP record route options. Who knows about that option? Yeah, there's not very much. How many people know how traceroute works? Lots more. This is cooler. Because traceroute can easily be filtered. You can configure on a router, hey, I don't want to send any time to live exceeded messages because it just costs me performance. Just throw packet away and be silent about that. Record option is something you can't turn off on the routers. So you'll get them anyway. Drawback is you can only have the next 9 hops. So you must be near the target you want to traceroute to. Ping minus R, that's your traceroute alternative. Very cool. And not many people know about that. So the next change is there are no broadcast addresses. And this is bad. Broadcast makes life for us so easy. There are no broadcasts anymore in ipv6. What you have instead are the multicast addresses. Multicast means you can say any node, local, or just the local routers, or you can find all local NTP servers. That's pretty cool. If you want to know what NTP servers have on the network, just make a multicast request and you get the reply. That's very cool. But you can only ask them from local. So it's not like if you want to know, hey, what are the NDP servers in that city in Japan or that network, it doesn't work. No, only for your local network it works. Well, for some. There are some multicast addresses which are global, but these will be very experimental because this will be very easy for denial of service. So this is currently in the standard experimental and not being used. So as a result, it is a big problem to find remote systems. But now we get already to the next stage, which is reconnaissance. Reconnaissance in IPv4 is easy. A normal subnet size is 2 to the power of 8, so 256 IP addresses. So what you do, you do ping sweep of the target remote class C network. Takes about 5 to 30 seconds, depends on what tool you use, how far away the network is. Then you do port scan to the live host, and then you look for vulnerabilities on the active services, exploit them, and, well, happy Eastern. Wide range of tools available, Nmap, AMAP, Nessus, lots of exploits, blah, 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 blah. Okay. When we go to IPv6, this is not possible. The normal subnet size is 2 to the power of 64. It's not that much more, but a lot more IP addresses to scan for. I have no idea what the name is for that number, but it takes long, I can assure you. So, if you brute force and you think, okay, machines get faster, networks get faster, 500 million years until you have scanned the subnet. Great. Just that one subnet, which might have just one active server, okay? If you're being clever, like nobody will use privacy extensions, so we know there are special vendors manufacture their the Ethernet cards, so only the key space is reduced that way, so you can still somehow make this key space much smaller, but still will take some months. And it's still too long to do scanning, right? Who wants to scan for some month until to find out, oh, there are 5 machines on the network? Yeah, that's not good. So, but others have the same problems, namely the administrators of the network. They also have to know which machines are there, so they will have services available for that. So first, public servers will need to be in public DNS. Nobody will remember the IP addresses anymore. Any one of us who travel around, they know, for example, their primary DNS service they can always put in and be able to serve somewhere. You will not know the IP addresses of ipv6 DNS servers, right? So public DNS will in the future be the primary source of all information. And inside the company, all hosts will be in the private DNS, in the internal DNS. Otherwise, an administrator will not be able to know which systems are there, where they are placed, how to configure them. So, in a result, in the future, DNS will be the primary source of all information, so every hacker will go for the DNS servers, because there is no other effective way to find out which systems are there. If you're local on a network, it's easy, but you have to get there first. And to find out what systems are there, you will only have DNS and let's say Google stuff, find out what systems there, but from network side, it's DNS. We have some new opportunities like the standard multicast stuff to find out about routers, DHCP server, time server and stuff. Once you've compromised one system, it's trivial to find all other systems on the same network. That's trivial, but you first have to get there. After that, everything stays the same. So once you know the system, you do the port scanning, you do look which services are there, exploit them, blah, blah, blah. Yeah. But remote alive scans on networks will become impossible. And that's the basic point of that here. So I wrote some tool. I wanted to show it, but somehow on Linux I couldn't get the presentation to work, so I had to reboot to Windows, so I can't really show the tool. I wrote a tool which is ipv6, which is part of the toolkit, which does the following. It sends an ipv6 echo request, same like you can do with a ping6 command. What it also does is sends a packet with an unknown header, a packet with an unknown hop-by-hop option, and an IP fragment. The first fragment, because then you get an ICMP reply, oh, I can't assemble this packet. For that reason, because this you can turn off. just configure do not reply to multicast or broadcasters ICMP requests. This you can turn off. This you can't. Maybe in the future on some operating systems, but as far as I know, for these systems I reviewed, you can't. So there is always a way to find all local systems, whatever you do. And this is what this tool does. It has some other stuff like one-shot fragmentation and routing header options. I'll come to that later, because that was research I did, and that's pretty interesting. So, next topic is DHCP in IP version 4, and what is the corresponding in IP version 6. DHCP, everyone knows it, is used to get an IP address on the network. Anybody can run a DHCP server, so it's all trusted. You have to trust, otherwise you're fucked. If you're a rogue DHCP server, you can feed fake DNS servers, routing information, blah, blah, become man in the middle. Similar concept with ARP, Address Resolution Protocol, which is used to look up a MAC address if you know the IP address, which is important if you want to network connectivity. Anybody can send those replies, so this is a broadcast being sent to anyone. Hey, who has that IP address? And everybody who raises his hand, he might be the lucky one to get the traffic. So hackers always try to be first. How is this in IP version 6? There is no security added to both protocols. ICMP version 6 does not have ARP, and you usually do not need normal DHCP. So first, ICMP version 6 has stateless auto-configuration, which means as you have your MAC address, your own MAC address, you always know the host part of your IP address. Just what you need, it's the network part of your IP address. And routers send around, hey, I'm a router, this network should have this IP address range, and if you have 5 routers, everyone announcing a different IP address space, what area you will have 5 IP addresses. Yeah? Different network part, but same host part. This way, you automatically get your IP address. No need for DHCP anymore. Then if you want to know router, you already see the router advertisement, and you know that. And you know, okay, is this address, this is where it goes to, and what priority of the router it is. Also, there is no ARP anymore. Now it's also done with IP version 6. It was a clutch with ARP. Another protocol beside IP just to solve the IP, how to get the IP address problem, and that's not efficient. So what is being done is ICMP6 is now used to get the MAC address for an IP version 6 address. You do a neighbor discovery, and a neighbor solicitation request and says, oh, who has this MAC address for this IP address, and then anybody can answer and say, hey, it's that. What they also implemented here is a duplicate address detection. So whenever you get a new IP address, you make a request, does anybody has this IP address already? And if nobody answers, okay, I can use it. So how does this work with the stateless auto configuration? If a client needs that message, he can just request it with a router solicitation request and asks for a router advertisement. This FF002, this is the multicast address, all local routers. So if you ping this address, all routers on your local network will answer. That's pretty nice. ICP type 133. And any router on the network will then answer with a router advertisement reply. And there will be the network part, the prefix, lifetime, and so on and so on. So this is basically DHCP Lite. You don't have the DNS servers yet, but you can find them with another multicast. So who is the DNS server here? So that's pretty easy. So there is no real need for DHCP anymore. And it doesn't mean, it's not important how dumb the machine is. If it's a toaster, if it knows IP version 6 can get on the internet. But anyone can send those router advertisements. And I wrote a tool for that. And this tool tries to be a little bit clever because you can set priorities on routers and stuff, and it always claims to be the highest priority. So it will usually become the default router on the network and get every traffic. So neighbor discovery is like an IP version 4, ARP request, who has his has his MAC address. Same here, you have a neighbor solicitation request, ICMP type 135. You send it to everyone on your local network who has this IP address. And then the owner of that IP address sends an ICMP type 136, which is neighbor advertisement, and says, hey, this is my MAC address. So you might know the tool Parasite, which I wrote 5-6 years ago about ARP man in the middle tools. This is now Parasite 6, which is the same for for this attack. It just claims to have every IP address on the network and tries to be very fast. So sometimes it's faster as the kernel, sometimes slower. It also depends on the network speed and stuff. So I did it over wireless, and I was still able to get to redirect some traffic yesterday on my machine. I had to test it, so sorry. So, works very well. Yes, I come to that later, and why you will never see that. That's what's in the design spec. Yes. The question was that this can be secured by ipv6, and I said yes, that's what's in the specs, but you will never see it. But I come to that later because that's an important point, and that's why it's still all the vulnerabilities are still in there. But I come to that. Don't worry. The duplicate address detection works exactly the same as also solidization question says, who has this IP address? And if nobody answers, it just assumes, okay, nobody is using that. Well, I wrote another tool which just says, hey, I have this IP address, I have this IP address, I have this IP address, and well, Windows is very happy about this, not allowing you on the network. I can tell you, Linux doesn't care. Linux has the worst implementation IP version 6 I've encountered. Every other operating system, including Windows, is better. It's so bad. It's really the worst implementation I saw on IP version 6. Stuff is not working. Animated implementation error, I'll show you that later, because this can be used for nice smurfing. But only Linux. All others are fine. Oh, we already at smurfing. Oh. Okay, smurfing. Smurfing is a very interesting misuse of broadcast addresses on the internet. You send a packet to a broadcast address, so like a ping request, and you get lots of replies. Because usually, well, most operating systems send a reply to a multicast echo request. So what people were doing, send those requests, but spoofing the source address of your request for someone you didn't like. So he was getting all the replies. And this was very nice to fill up their network connection and DOS them. If you want to smurf an IP version 6, it doesn't work because there are no broadcast addresses. And the usual multicast addresses are link local only or site local only. It doesn't really help you. There's an RFC which states that ICMP response should send when a destination was a multicast address. There are some exceptions where a response to a multicast packet is being made. There are two big Cisco security documents which says these are the vulnerabilities in IP version 6 and we have to handle. And they said, oh, this is not a problem. Yeah? But if you read the spec closely, there are exception made and they got it wrong. And there are nice ways to exploit that. Locally, you can always smurf, but this isn't real because you're smurfing yourself too. It will only help you if you hack a local machine and then smurf the local network. Well, great deal. You can always DOS your local network, doesn't matter how. Remote depends on implementation on routing headers and fragmentation and stuff. I wrote two tools for that. One is Smurf6, which just does the local initiated smurfs, so it just floods the local all nodes multicast address, so it's nothing really special. And then I did rsmurf because I found a vulnerability in the IP version 6 implementation of Linux. Oh, big surprise. So it's reverse smurf because it works differently. You just send a ping request to some Linux box. His real destination, so not a multicast, broadcast, whatever, no, to his IP address. However, a source address, you specify the multicast address for all nodes. every other operating system says, oh no, I'm not doing that, I'm not dumb. Yeah. Well, Linux is sometimes different. So what happens? You can smurf from remote with that very easily. And there's nothing you can, maybe hopefully they will do a kernel patch for that to remove that vulnerability. Or it's more of a logic error, not like, oh, it's crashing. So I don't know if we will really see that. So from remote, if you have a system with 100 Linux servers, you send one packet, you can locally 10,000 packets. So this can be very, very cool. Okay, but I'm not a big fan of denial of service stuff because that's just lame. So let's get to the routing protocol stuff. In IP versions, well, normally the routing protocols provide their own security mechanism, like MD5 authentication on OSPF, BGP and stuff. This does not change in IP version 6 except for OSP version 3. And now we come back to that question about what about IPsec? IPsec is included in IP version 6, so it should solve all your problems. In theory, yes. OSPF, the working group, also thought, hey, IPsec is there. Let's do that. They should do authentication and encryption. So why caring about that? So if you use OSPF in IP version 6 and you don't have IPsec, there's no security whatsoever. And this will be a problem because OSPF is, in my opinion, the best local area routing protocol and lose lots of network. But if you change to IP version 6, you should change your routing protocol. So now let me tell something about IPsec. IPsec is part of the protocol. Everything's there, so why not using it? The main problem is always encryption is key distribution. How do you get one key to another person? If you're within a company, this is something maybe you can manage. You can have a certificate authority, you can put the keys into DNSSEC or whatever, and there are the keys. If someone wants to encrypt to someone, he requests the key and then encrypts stuff. That's okay. But on the internet, you will never ever see that. Who will be holding the keys? Yeah, Americans would say, yeah, we will have the keys, trust us. Europeans will say, never, never, ever. Chinese will say, I will. Okay. So you see the problem. Nobody will trust the others that they will handle it nicely. So this will take 20, 30, 50 years, if ever, until we can deploy IPsec globally on the world. So this is why we will not see it. We might see it in some companies who are very aware of the problems, but then again, you will see implementation problems. Implementation problems are that it will slow down everything. Just to get the keys, to distribute the keys, this will be a big problem. There will be another problem I will show you later when I go to visioning what will be problems in IP version 6 when we use it. So then you have routing header manipulation. And this is basically source routing in IP version 6. You have a server and there's a firewall in between. You would like to access, let's say, the admin web port which is there but is not allowed by the firewall. No communication to this IP address is allowed, but you may access the other server. So with source routing, you could say on IP version 4, please give the packet to that machine, and if it receives it, remove the IP address, put another target in, and pass it on. Same is in IP version 6, the routing headers. Exactly the same. And you can do the same here. So what firewalls usually have, or routers also, is they don't allow source routed frames. But there are ways around that with IP version 6. There is in iLive 6, or not /remote, I also implemented in this, so this is not an extra tool anymore. You can just specify, do routing headers, specify as many IP addresses as you want, where it should pass through, and then you can do this attack to do a live scanning. Fragmentation. Fragmentation is very cool. So first, they fixed a big problem in IP version 4. You saw this speech of Dan Kaminsky, I think, where he said, oh, it was so bad. Why should a router in between do fragmentation? This is fixed. In IP version 6, a router in between does never fragment. If the link the packet should be going over is too small, you just say, oh no, wrong MTU size, resend please. This is how it should be done. So, problem solved. Still, of course, you can do fragmentation as a source. If you're the system which sends the packets, you can do fragmentation. So we have the same problems like, what can we do with reassembling? What if packets overlap? We can play the same games. But we can do one more thing. Don't have it in this slide. No, this is not in this slide. I'll come back to that later. Because there's something very nice you can do with fragmentation and routing headers. This is something you can experiment here on CCC with, I'm showing you now. So watch out. Here you have your firewall. You do ipv4 and try to get a public server, for example, to the telnet port or whatever, or NetBIOS, and it's protected by the firewall. They say, hey, I don't allow this. What people don't realize, and this is the same for many people configuring their own OpenBSD, FreeBSD, Linux, filter rules whatsoever, the ipv6 is a complete different part of the kernel. So just because you have a drop all rule as default, it's not affecting ipv6. So, if you don't have special filter rules by ipv6, you bypass these rules. So if you can connect somehow to a system via ipv6, good chances that you can get through, can bypass the filter rules. You can try it here. It works. I tried it on some. Most have it because people use something like SUSE firewall, for example, where this is already, if you just use SUSE firewall, it sets ipv6 rules, for example. Red Hat does the same as far as I know. But if you do your own rules, you will usually forget this because you don't know. Yeah, and it works. I tested it here. So, this was basically what are the vulnerabilities in ipv4 compared to an ipv6 and how to exploit them. So, this is just one page which should make you one thing clear. Also, ipv6 should be much easier to implement, but this was one of the design goals. If you see this list, you will see it's not the case. This is a very small excerpt. If you look on Bugtrack ID list on Security Focus, I found over 50, so I verified them that are really ipv6 related, 50 ipv6 vulnerabilities so far. And not everything is ipv6 enabled already. There are so much things you can do wrong, even if the protocol is easy. And if you take a look what kind of bugs these are, you will see, hey, I've seen it before. There's one important lesson people don't learn. Learn that. So, research and implementation tests. I did limited implementation tests because I had not that much time, because I did a presentation originally for Japan. So I was tested what's the Linux 2.6 kernel, Windows XP Service Pack 2, Cisco iOS 12, and FreeBSD 5.3. And see, for some stuff I said, how does the system would react to this? By the way, you can also look for denial of service stuff, like if I put these option header in this way, can it crash? I didn't look for that stuff because a fix and it's gone. But there are stuff also in OpenBSD, I can assure you. It's not the point here. Responding to packets to multicast destinations. So this is something you usually can turn off by an option, so I don't want to answer that. By default, Linux and FreeBSD have them open. So if you send a multicast ping request, you get an answer from these two systems. That's not really a security problem. It makes things easier, that's basically it. But I just wanted to see what are the defaults for the systems. Responding to packets with a multicast destination, same as here, but not doing an echo request, but putting in an invalid header option. So it can be ICMP, TCP, UDP, doesn't need to have any upper layer protocol in there, doesn't matter. If you just put an invalid header option there, they all respond to. And you can't really configure that off. So by this way, you can find all local systems, always. Responding to packets from multicasters, this was the remote smurf I was talking about. Only Linux does that. Only they are dumb enough. Routing header to multicast, this was a very interesting idea. Well, I thought, hey, we don't have broadcast addresses. I still would like to trigger the remote multicast address. So what I can do, I specify a routing header. So I get to the target network, and then say, forward this frame, please, to the local multicast address, all nodes. Yeah? Sadly, they all didn't want that. Otherwise, it would have been very, very cool for remote scanning. But sadly, didn't work. But I found another thing which is cool. Fragmentation and following routing header. This can be used to bypass firewalls and routers and whatever. If you have a Cisco, if you have Solaris, if you have Linux, doesn't matter, and use them as a router, you can say, don't forward source routed frames. And then any packet which has a source routed option is just thrown away. Yeah. You can do this with ipv6 too, but if you put fragmentation before that, you can even do one-shot fragmentation. One-shot fragmentation means you specify this is the first fragmentation, so starting at 0, and set the flag this is the last fragment. It doesn't really make sense, but they all eat that. And afterwards, you put the forwarding routing header. All in between says, oh, no, there's no forwarding header, I'll pass it along, that's fine, it's fine, until to the target system. Target system does the defragmentation. Hey, there's a routing header, let's honor it. And uses it. And all are vulnerable to this, even Cisco and stuff, and that's pretty cool. So if there is security on your ISP, you will always be able to bypass that and use routing headers. That's pretty cool, because source routing, you know ISPs where source routing still works? I don't know one, there will be very few, but on the internet it will not work. In the future it will work again. That's cool. So that was the one-shot fragmentation, all are vulnerable to this. So I only did very limited research, and because on very limited time frame, because I have another project which I'll show you afterwards. So what will be future research from THC on that? Global multicast exploitation, which is FF0E. This is global multicast stuff, like what are all the NTP servers on the internet? I will do some more research on that because this will be much fun. MLD, which is a multi-listener discovery protocol, version 3. It's not very security sensitive topic, but it seems there is some interesting stuff you can do with that. And ipv4, ipv6. There are different ways on how to migrate from one to the other. And there are vulnerabilities in there. Some have been found already in the protocol specs. Oh, you can do this and that. But there will be more. The problem is there was not much research time spent to this already in the security community. So there will be more. And we will also put some time on that. Okay, so upcoming, so this is more the vision stuff. So what will be the future? There will be specialized attack tools for ipv6. But the basic note is it will not be much different from what we already have in ipv4. So there are not more vulnerabilities or more threats we have to work against. Worms will be much of a different in ipv6. TCP/IP worms like Slammer, infecting everything within 20 minutes, the whole internet, will not work because of the large IP address space. So they can't use that simple technique. So they will do other stuff. Email worms will stay because this doesn't change. Messenger P2P worms will come because it's easier to spread. Why this means, these worms will more use like public DNS information, trying local search engine stuff. So these will change, but they will become much rarer. And DNS servers become the primary target because that's where all the information you're interested in will be in. Attacks will move more to clients, where you attack one local system and then you attack the rest of the network from there. So not like usual, oh, let's scan the whole range, oh, there's a vulnerable service, oh, I'm in all 3 systems. This will not be the case. You will have trouble finding one server, and this will use the web server, DNS server, something which is public. Attack this, trying to compromise, and if you achieve it, then you go local. So this will be the future penetration test methodology. When IPsec is widely deployed, if. So within a company or worldwide, which will be 20 years in the future, certificating will be a primary security concern because this will be impersonation. Yeah? So if you attack a system, if you compromise them, the first thing you will do, you will try to steal the certificate to be allowed on the network. So this will be important then. Okay, so conclusion. So far, no new risk in ipv6. Some improvement against ipv4. It will have a strong impact on the hackers and also on the administrators on how they have to administrate their network. If you have IPsec, it will not ipv6 really secure. It will make attack tracing easier. It will sniffing man in the middle, very difficult. But web application will still be vulnerable. This will not have no impact at all on that. If you take a look at ipv6, first it looks very easy, but the more you read about it, the more you research about it, it gets so complicated. That's why it's not much research from people there, because it's just so much. Even for the new hackers who will come in the future, who don't know IP4, trying to understand IP6 in the first place will be very tough. So if you start, oh, this is IP6, I try to learn it, I'm new, this is hard stuff. So, very short questions, and then I do a 10-minute presentation on the other new project. Questions? Yes?
Right, so from your point of view, seeing all the vulnerabilities and all the issues we have there, what are your 3 key recommendations? You would have to actually secure a network apart from turning it off, obviously. And IPsec was obviously one if you do it within a closed network. But apart from that, what would you recommend to do if you want to secure your network and use IP6, version 6?
Well, for security, if you move from IP4 to IP6, you gain a little bit more security. So it's better to move to IP6 than stay in IP4 for security. Well, what you can do to enhance, well, do the IP6 configuration on local machine secure, so turn off this, turn off that option and stuff. Enable IPsec, configure your filter list correctly, and do good host security, and protect your DNS servers. That's basically it. This usual stuff. This does not change. I mean, that's the main topic. It just fixed minor stuff, put some little new stuff in, but this has no really a security implication. Yeah. So, other question? So the question was, for those who did not understand it, what about mobile IP6? Did we also look at that? This should have been on the research stuff, because there are different techniques on how to update on mobile IP6. So I'm now in this location, please send the packet here. Now I'm that location, please do that here. So there are different solutions to this with routing headers and stuff. But no, we haven't looked into that yet. But we'll do in the future, because it will be very interesting. Yes, another question?
Are you aware of any packet filter that's able to strip off source routing functions?
No. That's a good thing about that. Well, you can implement it in a stateful firewall, of course. But normally a firewall just throw the packet away or leaves it through, and it's not reconstructing.
Yeah, but you have to step through all the
yes. Which should be easy, but you can still get that wrong, as we saw in some of the vulnerabilities. Okay, if there are more questions, just drop by afterwards. So, we've got 10 minutes left for the second presentation, which was, sorry, I have to skip back. I'm not very happy with the current code state. As I told you, I would like to shoot the implement guys on the kernel on how they do some stuff. It's really horrible. So it's not on the usual public release stuff like thc.org. It's kind of hidden. I hope to have it in more. So the code works, yeah, but there are some limitations. And I try to get rid of them, but until then, I will not officially release it on the website and say, hey, it's a cool tool because of the. We have some quality. We like to have some quality in our tools, and this is not meeting our normal standards. It does its job, but could be more effective. So that's why it's somehow hidden here. Note that down, if you want to have it. Okay, I'll leave that here for a minute and just tell you what the next small presentation is about. Who of you know war dialing? Hands up, please. War dialing? Well, hey, that's pretty cool. I mean, it's a hacker conference, of course. And who of you know THC scan or use THC scan? Some of them? Okay. War dialing is not that much used anymore. For I have no understanding. It's much more fun and much easier to hack than doing TCP stuff, because no one looks for their modems. So, THC scan is very old now. We had our 10th birthday in October, so I did an update to the version to have some, well, presents for the public. But still, we are in the internet age. So things have to change. War dialing is still interesting, so how could we do that more efficient? And so the idea of THC scan next generation was born. It's completely different. It's not like, oh, you just upgrade to this and everything is fine. It's something completely different. It's a complement. So THC scan was a war dialer for MS-DOS. You can even use it today with a PC emulator, works perfect. So what was it? 2 years ago, Plasmid, one of our members, sometimes we make internal challenges, so can you make that? And he was able to run it on his Mac OS via the infrared port on his mobile phone to dial 0800 numbers. So it can still do that. It still works. It cannot be ported or updated or anything, it's Turbo Pascal. 10 years ago, that was the main language to use. Yeah, not today anymore. So the coding idea was a war dial for Linux and Windows, so this is not important, of course, that's the standard today, but support as many modems as you can find, so having 10,000 of modems connected to one war dialing system, do distributed scanning, do detached scanning, so you connect somewhere, say, hey, please scan this range, then you log off. Going there some days later, oh, give me all the results. Have GUI command line, have database support, have voice over IP support, carrier identification, carrier hacking, and scanning large ranges of numbers. So what I want to get to that I can scan completely 0800 in just one command. So this is my goal. But this takes lots of CPU power, RAM resources, and hard disk space. So this is kind of a challenge. The basic concept is like this. You have your client, who connects to the master. The master is the brain, controls everything. Every modem you want to do war dialing will have its own zombie controlling that modem. Just one zombie for one modem. And you tell the master, please connect to this zombie and also use that in war dialing. And the idea is that you can transparently say, hey, at this modem, at this morning, in the middle of scanning, remove modems while scanning, doesn't matter. It works perfectly, no problem. And all of them in the future have a THC scan like local GUI, which directly connects to a zombie. But that's really optional. So the basic concept is client, a master, and a zombie. So today, we have it working, just only the command line tool, no GUI yet, but the GUI is not really needed. Commands are simple. You can just use telnet to control everything, like connect, which connects just your system to a master. With add and delete commands, you add or delete modems or zombies. With this command, you just start scanning a whole range. You can cancel them, can get more output. You can dump the replies, you can see what's going on. You can see all the replies of all zombies if you want to. You can see, oh, how fast is the status of that scan? Has it then already started? How many numbers are already dialed and stuff? I wanted to show it live, but with Windows, it's much harder to set things up. The server listens for clients. You can connect with as much as 100 clients, doesn't matter. Does all the connection pool for all the zombies, for all the modems, splits the scan ranges to the zombies in chunks, so every zombie gets some numbers. And before the numbers are depleted, it sends more numbers, so there's never a lag of, oh, I need something to scan, I don't have anything anymore. So time is efficiently used. Keeps control which number has been scanned. Busy numbers are redialed up to a number you can define, like say, if the number is 3 times busy, don't dial it anymore. And they are not redialed immediately, but later, so it's done intelligently. It saves data in reports. Important thing is, only this master knows about the scan results. Clients don't, well, they can log their stuff, but they have no intelligence. Everything is done on the master. The zombie is pretty dumb. It can just operate the modem and talk to the master. That's it. This keeps things very, very easy and very portable. And verify to work is, for all 3 components, Linux, Windows Cygwin, it works perfectly, and Mac OS X. Works fine. So, upcoming versions. So, the basic functionality as you see it is done. It's still proof of concept, it works, but is this more of an alpha or beta release? Stage 2 will be that it has SSL encryption and challenge response authentication. We'll have carrier identification, remote modem configuration, and some other missing features like, hey, scan these numbers in a text file. Blacklisting, prefix restriction, blah. Stage 3, which is scheduled for pH neutral in next year, automated login hacking, SQL database support, and now it gets interesting. Stage 4 is planned to have voice over IP support, which means you have a tool where you have the information, so this is my SIP gateway, just give that information, it dials, just without a modem, just with TCP IP to a SIP gateway. You get a WAV file in reply, which is busy signals, whatever, our modem carrier, and then we do some FFT stuff to identify if there's a carrier or not. So, war dialing without a modem. This will be cool, and hopefully a GUI. I'm looking for someone who would like to do that, because I'm not a GUI guy. So whoever would like to do that and join the project, it's open for everyone, especially for the GUI. And stage 5. Stage 5 will be very special. Stage 5, I will release next year, is a community master server. So, anyone can join that master server. So, can get an account from us, can add their own modem, and then by that we can have large number of modems available. Lots of stuff in here, so it's very, very complex. So what basically happens, if your modem is used as in a war dialing, and you can say just dial 0800 numbers with my zombie here, nothing else, so no cost for you, you get credits. So once you have acquired enough credits, you can start your own war dials. So let's use all the network to scan these numbers. If the result should be placed in a public database, anybody can see that these results, and it costs less credits. If it's just for you, nobody else should see the results, it costs you more. Yeah, so this is a basic concept. So you can have lots of modems connected together, have good authentication on that, have a public database, have lots of fun. Yeah, so that will be the community project. Will there be security in there? Of course. In the next version, SSL, challenge response authentication, stuff, of course. Questions? If not, thc.org, it will be downloaded on the 1st of January. You can already download it from the project page, which is www.thc.org/thc-tsng for THC Scan Next Generation. THC-tsng. Well, that's basically it. I made it in time. Thank you very much.